All right, this video is going over the second part of the work power energy unit, which is the energy portion. So let's get right into it and get into some definitions here. First of all, there's energy. What is energy? Energy is the ability to do work or the ability to exert a force. When we are thinking about energy, you have to have energy in order to have work happen. And that is why work and energy are actually both going to have the same unit, which is the joule. There are several different kinds of energy. The two that we are going to focus on are kinetic energy, or the energy of movement or motion, versus potential energy, which is stored energy. And again, there's a variety of kinds of kinetic energy, and we're not going to get too specific on as in terms of what type. We're going to mainly be focused on mechanical energy, but kinetic energy includes thermal energy or heat, mechanical energy, which is objects in motion, electrical energy, which are energy particles moving through a wire, and magnetic energy, which is energy causing push or pull. As far as potential energy, the one we are focused on is gravitational energy. So object stored when an object is, energy stored when an object is lifted above the Earth's surface. But there is also nuclear energy, which is stored in particles, elastic energy stored in things that are stretched, and chemical energy, which is what's stored in the chemical bonds. And then, of course, there are other forms of energy, sound and light, which we are not going to get into in this particular unit, but you will get into that next year. All right, so starting off with potential energy. Potential energy is the energy that is stored in an object. So when an object is lifted to a certain height above the ground, because gravity is pulling down on that object, there is the potential of it to fall, but because it is being held, that potential has not yet been realized, so that energy is stored. It depends upon the position of the object. The higher off the ground it is, the more energy it has stored. So the equation for calculating potential energy is the mass of the object times gravity times the height at which the object is located. So mass times gravity times height will give you the amount of potential energy stored in that object. And as I said, energy is also going to have the unit of joule. Now, the triangle is a little bit more complex than we had before. You could automatically switch this into being 9.8 if you wanted. You could make it 9.8 m times h. Just to remember that the gravity, at least for the problems that we are doing, unless you were told otherwise, gravity will be 9.8 meters per second squared because it is happening on Earth. But you may also want to just write down the alternative forms of these of this particular equation. So the first form is the original form, mass times gravity times height. That's our first form. Another way you could write it, if I wanted to solve for mass, it would be mass equals potential energy divided by gravity times height. Just make sure to multiply that gravity and height first before dividing potential energy by it. And then if I wanted to solve for height, it would be potential energy divided by mass times gravity. And again, in all of these cases, we could switch out gravity automatically for just 9.8 here, because for the problems that we will be working with, we will be sticking with them on Earth. Okay. All right. So let's look at a problem. So we have a 65 kilogram rock climber is climbing a cliff. What is their potential energy when they have reached the height of 35 meters? If I wanted to go ahead and solve for this, going ahead and listing my variables, I'm looking for potential energy. I know the mass is 65 kilograms. Gravity is going to be 9.8 meters per second squared. And the height at which we are looking at is when they are at 35 meters. So I can plug that into my equation, and I get that the potential energy is going to be 22,295 joules. So that is the potential energy. Now let's talk about kinetic energy. Kinetic energy, unlike potential, the object must be moving in order for there to be kinetic energy. So it's the amount of energy a moving object has. Now, kinetic depends upon its velocity. The faster it's moving, the more energy it will have. So as it's dropping, because gravity is an acceleration, that does mean that as an object falls, the longer it's falling through the air, the faster it will go until it reaches a point at which it reaches the critical point where it will no longer increase in speed. But we rarely will see that. You will see that with like skydiving and things like that. But just basic day-to-day, an object falling off a table or doing an egg drop, it's not going to reach that critical speed. So the equation for kinetic energy is a bit more complicated. We have kinetic energy is 1/2 mass times velocity squared. Now just velocity is squared. The mass is not squared. You want to square your velocity first, then multiply by the mass, and then multiply by half. Again, our units for this is going to be in joules because it is an energy. Okay, so if we were to type these equations, we would have kinetic energy equals 1/2 or 0.5 times mass times velocity. And I can't do the little squared here, so I'm just going to do the caret. Or actually, I'll just do this. Velocity times velocity, because that's another way of doing velocity squared. If I wanted to find the mass of the object would be, okay, kinetic energy divided by 1/2 times velocity. Okay, and then finally, the last equation. Oops, I keep doing that. Okay, we're just going to do this. All right, the last equation is going to be kinetic energy. Oh, why won't you let me work? Hold on. Sorry, I'm having a little bit of technical difficulties here. Oh, there we go. Okay, so if I wanted to find velocity equals square root, and I don't have a little symbol for square root, so I'm going to try and draw it in after, but it's going to end up being the square root of kinetic energy divided by 0.5 times your mass. And again, want to get a little square root symbol drawn in there. There we go. So that's how you would find the velocity. All right, so let's look at an example problem here. So we have a 35 kilograms kid skateboarding down a hill, reaching a velocity of 2.5 meters per second. How much kinetic energy do they have? Well, we have kinetic energy, we have the mass is 35, and we have velocity is 2.5 meters per second. So I'm going to plug that into my equation. Kinetic energy is 0.5 times 35 times 2.5 times 2.5, or that's my velocity squared, which gives me a total kinetic energy of 109.38 joules. Okay, final concept is what we call the conservation of energy. Energy, much like matter, cannot be created or destroyed, only changed. So, for example, if an automobile is moving, it is changing chemical energy into mechanical energy and heat energy. So the gas is being combusted, producing heat, but that combustion is also what is firing and allowing the wheels to turn. So in every situation, it may seem like energy is disappearing, but in reality, it's just being changed from one form to another. So mechanical energy is the total amount of kinetic and potential energy in a system, meaning in a situation. When we talk about systems, we're talking about whatever situation is that we are looking at. An object will have the greatest potential energy when it's at the highest position, so at its highest height, and it will, have its greatest kinetic energy when it's at the highest velocity. So if we look at this situation here, the ball at the top of the hill has all potential energy but no kinetic energy. As it starts to roll down the hill, some of that potential energy has turned into kinetic, but it still has some potential until it reaches the bottom, at which point, if there is no height, there is no potential energy, and it has turned 100% into kinetic energy. So as it rolls, the potential turns into kinetic until it reaches the bottom of the hill or reaches the ground, at which point it is all kinetic. But the total amount of energy stays 100% the same. From the amount of total mechanical energy here is exactly the same as it had here. So let's look at this example. A skier moving downhill, going on a jump, and we're going to look at how its potential and kinetic energy changes. So to start off, we have that our skier here at a height of 100 meters has we're given a total potential energy of 50,000 joules. They're not moving yet, so their kinetic energy is 0. Now, in order to move on and see how much kinetic energy there is here, a couple of things I'm going to want to know is what the mass of the skier is, because I will need that at some point. So if I know that mass times gravity times height gives me my potential energy, then I can get the mass of my skier by doing the 50,000 divided by 9.8 times 100, or divided by 980, and that gives me 51.02 kilograms. So I'm going to need that for later on down here. This one right here is probably the easiest one to go about solving. If I want to find the kinetic energy of my skier at this point right here, I don't know the height, but I'm given that the potential energy is 30,000. Well, since I know that the mechanical energy is my potential energy plus my kinetic, the total amount of energy is 50,000. So if my potential is 30,000, then I know 50,000 is going to equal 30,000 plus whatever the amount of kinetic is. So I subtract 30,000 from both sides, and I get that my kinetic energy is 20,000 joules. So they start off with all 50,000 in potential, but when they reach this point here, which is about 60 meters high, it has turned from all potential to having 20,000 joules of kinetic and 30,000 joules of potential. Then they reach this point here right before they jump. They're at a 30 meters. So at this point, I'm going to take the mass of my person that I calculated before times 9.8 times 30, and I get that my potential energy is 15,000. So once again, to find my kinetic, I'm going to subtract the 15,000 from my 50,000, and I get that at this point, 35,000 joules of that energy is kinetic, 15,000 joules is potential. Okay, take a second and calculate the kinetic and potential at this point here when they're in the jump. You can pause the video and then do your calculations, and then we'll talk about the answers. Okay, so you should have gotten that your potential energy was 30,000 and your kinetic energy was 20,000. Again, it's the same height here that we're here. So the value is going to get, as they go up, because they're increasing in height, their velocity is going to be slowing down, and they're going to be increasing their potential energy, decreasing their kinetic until they land, at which point it's turned 100% to kinetic energy. All right, we have one more example here, and then we are done. Given the boy's mass is 60 kilograms and he's moving with a velocity of 8 meters per second, we're going to find all of the missing values here. So right off the